Good afternoon. It's my pleasure to welcome you all to today's event, the Connecting Generations Thought Leader Talk. I'd like to extend a warm welcome to all our guests joining us from around the world and as well to everybody in the room today. I'm Dr. Jason Hilton. I'm a lecturer in social statistics and data science here at the University of Southampton, and I lead on the Connecting Generations research strand of modelling kinship and quantifying the connections between generations. And it's for that reason that I'm delighted to be able to welcome Professor Hal Caswell to give this lecture. So Hal is a professor in mathematical demography and ecology at the University of Amsterdam, and his research focuses on the use and development of matrix population models. And his influence on that field has been so extensive that I can confidently say that he wrote the book on the subject without any fear of contradiction. He also has received two advanced European Research Council grants on that subject, the most recent of which is on formal demography and kinship and families. And in the work that he's done on that project, he's developed a formal demographic structure for understanding kinship at various different levels of aggregation. So Hal is here to tell us today about this exciting work and discuss the insights that he's gained while doing that. And we also have a panel of Connecting Generations members made up of Professor Jakob Biak and Dr. Joanne Ellison, and we're delighted to be able to have them here today to give us our insight as well. And after that, we'll have questions from the audience, both in person and online. So do get thinking about what questions you'd like to ask and add them into the discussion. So without any further ado, I'll hand over to Hal for his talk. Thank you very much.
So, hello, and thank you very much for the introduction. Hello to the people here. Hello to whoever you are out in Zoom land. I cannot see you at all, so you're on your own. But you do get to ask questions. Let's see. Yeah, we're going to talk about formal demography, and that's formal demography is a field that looks for and studies relationships between demographic things of interest and the factors and processes that determine them. And the goal is to find relationships like that that are what you might call formally true. That is, they're true all the time, independent of particular places or times. So think of the life table. The life table lets you calculate life expectancy. That relationship is true no matter where the life table came from. Different places, different life tables, different life expectancies, but the relationship stays the same. The other thing that formal demographers like to do is to be able to extend things. The life table not only lets you calculate life expectancy, but a host of other things. It can be generalized to include multiple decrements, different causes of death, a whole range of things. I'm trying to do something similar to that with kinship. And what I'm going to do today is to quickly go through the basics of this formal demographic model for kinship and take a very brief look at some of the extensions of that basic model and spend some time talking about a piece of the story that I'm working on now having to do with generations and the connections between them. Since this is a Connecting Generations talk, that seemed like it would be appropriate. So this is a picture of a kinship network. It's centered around a focal individual, which I will call focal, and that's in the middle. And then you can see daughters, granddaughters, great-granddaughters going down, mothers, grandmothers, great-grandmothers going up, and siblings and aunts and cousins and nephews and nieces and other kinds of kin. This network could be extended as far as you want, but this is one that I've been working on. The letters represent different kinds of kin. I use them as symbols in the equations. Other than that, they have no particular meaning. And the goal of the exercise is to find a relationship between the mortality schedule, the fertility schedule that individuals are subject to, and how that generates a network of relationships. So, is focal centered? Let's meet focal. Focal is an individual from a population. You can think of that she or he has some specified age that we're interested in, lives in a population with a specified mortality and fertility schedule, and population that has some distribution of the ages at which mothers give birth to their children. So, the insight, the place that gets this going is the insight that the kin of focal are a population. This picture is a part of the population of my kin, taken at a family reunion a few years ago. I'm somewhere in the back of this. You can see that this population has different ages and, well, they're different, let's put it that way. If the kin of focal are a population, then we might as well model them as a population. And we do that with population projection. This is the most basic kind of population calculation that there is. And in this, I wish I could point to it, but I can't really. But if you look on the left, there's a vector with the numbers of individuals in 3 age classes. This could be many age classes, that wouldn't matter. And that vector at time t plus 1 is obtained, look on the far right, there's the vector at time t, by multiplying it by 2 matrices. One I will call U, and it includes the survival and the transition to different age classes of the individuals. And the other one that I will call F is the fertility, the production of new individuals by the reproduction of the individuals in the different age classes. And you can write this economically as a matrix equation without having to fill in all of the numbers. And that projects the population forward in time, given that you know the fertility and survival matrices. What about kin? So let's use K to represent some arbitrary type of kin. Daughters, siblings, whatever. Then the model for the kin of focal as a population is that age distribution at age x plus 1 of focal has 2 pieces. One is the survival of the kin that focal had when she was age x. So that's U times K of x. And the second term, which I've denoted by beta, is a reproduction term, a recruitment term. Kin populations are different in some ways from what we think of generally, because new kin come from other kin. The reproduction of focal's daughters doesn't produce more daughters, it produces granddaughters. And so each type of kin has the potential to get a recruitment term from some other type of kin through fertility. And you use the fertility matrix applied to the other type of kin. Some kin have no new recruitment. Focal doesn't get any new mothers after she's born. This is the example for the daughters of focal. That's A in the kinship network diagram. And you just work through each of the pieces. What's the initial condition? How many daughters does focal have when she's born? This will be on the exam. 0. Sometimes we get nice clear answers. Where do new daughters come from? New daughters of focal come from the fertility of focal. And so we have the beta term coming from the fertility of focal. And we can do this for mothers. We can go through every one of the kinds of kin in that network, and there's an expression for the initial condition, and there's an expression for the recruitment term. Easily calculated just on any kind of computer. So, what are we going to do with this? We've got this. What are we going to do with it? We can do all kinds of cool things with it. Here's an example. just to look at one kind of kin, comparing one population at two different times. Japan, under its 1947 rates, had a very low life expectancy, 54 years, and a very high total fertility rate, 4.6 children per woman. By 2014, the life expectancy had increased to become certainly one of the longest in the world at 87 years, and total fertility rate had dropped below replacement to 1.4 children. This shows the expected number of daughters of focal individual in Japan under those two rates. The red line is 1947 rates, the blue line 2014 rates, as a function of, on the x-axis, is the age of focal. Under 1947 rates, focal starts producing daughters, produces them rapidly, produces lots of them, and then they die off quickly. Under 2014 rates, she produces daughters more slowly, not as many, and they don't decline hardly at all until very old ages of focal. And you can look at all the other kinds of kin. This is the number of mothers surviving for focal, but I'm going to skip over that. Let's look at some extensions. What if we count not only the living relatives of focal, but the dead relatives, the experience of death of relatives? So we extend the vector by incorporating a vector with the age distribution of living kin and the age distribution of dead kin. We enlarge the matrices to include, there's a U in the upper left corner of that matrix, that's the survival of living kin. An M, that's mortality, that's the accumulation of dead kin. There's a 0 in the upper right corner to indicate that the dead don't come back to life. And we can do this, we can calculate all kinds of things from it. This is what the bereavement landscape looks like under Japan rates for 1947 and 2014. The red curve shows the cumulative number of deaths of daughters to be expected to be experienced by a focal individual of different ages, and it's large. Under 2014 rates, focal will probably never experience the death of a daughter. We can extend the model in other ways. Instead of just living and dead, we could incorporate some other kind of a characteristic, and we just enlarge the vector, we enlarge the matrices. Here's what the matrices look like. What kinds of things might we use? One easily thought about one is parity. How many offspring has a woman had? And in the human fertility database, there happens to be nice parity-specific information for Slovakia. Slovakia between 1960 and 2014 had a similar increase in life expectancy and decrease in total fertility rate. And here's the number of daughters, but now you see the same increase in the number of daughters and eventual decline, the decline being much more sharp in 1960 rates than in 2014 rates, but you also see it broken down by parity classes from 0 up to 5+. And the difference is not only the number of daughters, but parity, high parity women with 3, 4, or 5+ children have almost disappeared from the picture in 2014 rates compared to 1960 rates. So you get information on the family structure of the kin from putting variables like this in. What else should we do? We could let the rates vary with time, but time, in fact, will not let me do that. We could add sexes to the model. So I've been talking about female kin of a female focal individual, but we could put both males and females in, and then we enlarge the vector to include females and males. We enlarge the matrices to include survival or mortality of females and males, which is usually different. and the fertility of females and males, which is sometimes different. We end up with the same formal equation, except now the vectors and matrices have become bigger. And we get here, top row of this is now not daughters, but children. And you see the blue part is females and the red part is males for 3 countries that happen to have different degrees of male-female differences in mortality and fertility. Wow. Okay, let's see. We're moving right along here. There's more extensions. I mentioned time variation. You can put in information about diseases, information about causes of death. There's a R package implementation being developed by Diego Alvarez Gutierrez at the Max Planck Institute. I want to talk a little bit about lineages of generations. So this is the definition of generations that is the sort of biological one. An individual, their children, their grandchildren, their great-grandchildren, that is a sequence of generations. So it's not the boomers versus Generation Z kind of a definition of generations. So in this diagram that we had, if you look at focal, you see that going downward from focal, there is children, grandchildren, great-grandchildren. These are successive generations, and you could extend this down and we'll pluck that part of the network out, and we will see how it works. First decision you have to make is what constitutes a generation. So one way of doing it is, in the basic part of the model, is to do female descendants through female lineages or male descendants through male lineages. So this has been historically important in various kinds of royal family things. That would include focals, let's say daughters, granddaughters who are the daughters of daughters, great-granddaughters who are the daughters of granddaughters who were daughters of daughters, but single-sex lineages, or you can calculate two-sex lineages, where now focal can have daughters and sons. And focal's daughters can have daughters and sons, and focal's sons can have daughters and sons. And so you can see this keeps bifurcating, and there's lots more ways to grow generations when you count that sort of definition. Again, you build a model where you simply extend the vector of to include these different generations, K1, K2, big long vector. You can do 20, 30, 40 generations on a laptop. It's not a problem. You enlarge the matrices to include the survival of individuals within each generation and the fertility, where individuals in a given generation produce offspring who automatically become part of the next generation. You get the same equations for the dynamics of the kinship network. You have all the generations in the model. So if you're interested in connecting generations, then you have the option to build in interactions between those generations, because that part of the model is there for you to play with. Let's look at Japan again, right? So remember, 1947 rates, Japan was essentially growing like crazy. 2014 rates, Japan was not able, population was not able to grow. This shows projection of the first 10 generations of a single-sex lineage, starting off in Japan, and you can see under 1947 rates on the left, the generations are growing. You can see how much they overlap. You have, it's not shown here, but you have all the age structure information of these generations. So you can pull out from this, if you're interested, the way in which different kinds of age classes in the population overlap with each other. The right-hand side shows, somehow I switched to 2009 rates, but not that different from 2014 rates, and you see the generations shrinking, each one smaller than the one before. But again, you can still see the overlap. You could still consider what age groups were available to interact with each other between generations, separated by however many generations you want. So we have the ability now to do these kinds of projections from any set of generation-specific rates. That's fun. The other question that comes up when you think about generations is, do these lineages last or do they go extinct? Personally, I find it hard to think about the problem without finding myself thinking about things like The Lord of the Rings or the Game of Thrones, where the persistence of lineages down through the generations becomes an important issue. So how do you look at whether a lineage of generations persists or dies out? This is the oldest stochastic problem in demography. In 1874, the Reverend Watson and Mr. Galton analyzed this in the context of the extinction of family names in Britain. And that's a one-sex lineage because, at least then, family names would be passed down from fathers to sons, to the sons of sons, to the sons of sons of sons. And they wanted to know what determines whether family names die out and disappear or whether they persist. And the tool to do that is a particular kind of stochastic calculation called a branching process. Branching processes are fun, but we're not going to try to go into them except for you to be able to think about it as branching process is a model for a thing that makes copies of itself. In our case, the things are people, and people make copies of themselves. How many? How many copies? X is a random variable, and it has some kind of a probability distribution, and there's a probability generating function calculated from that probability distribution. And then a lot of stuff goes on, and you end up with a simple recursion relationship for Q of t. Q is the probability that the lineage has gone extinct by time t. We don't just have individuals making copies of themselves. We have individuals that differ in their age, or their age and their stage, or their age and their sex, or all these different possibilities. And so we need to do a matrix version of this kind of probability generating function. We can do that. You end up with the same recursion relationship for Q of t, which is now a vector telling the probability of extinction by time t of a lineage started off at time 0. Here's what it looks like. Here's the first ever results for this. On the left, Japan under 1947 rates. Remember, under 1947 rates, population was able to grow, and the blue line shows the probability of extinction by some time for the one-sex version of lineage, daughters of daughters of daughters of daughters. And it goes up. By about 200 years, it levels off at a little over 0.4 and is almost flat from then on, meaning that extinction, if it's going to happen, happens before about 200 years. After that, the lineage, if it hasn't gone extinct, has grown big enough that it's not likely to go extinct. On the right-hand graph, you see Japan under the 2009 rates. Oh, it says immortal. Ignore that. They're not immortal. And you see under 2009 rates, the generations were declining, and you can see that the extinction probability goes up and eventually becomes 1. If the population on average is declining, eventually it goes to extinction with probability 1. But if you define the lineages as both sex lineages, so you have that branching number of individuals, then you get the red curves. And the probability of extinction goes down, and even under 2009 rates, if you get to count your descendants, both male and female, through all the possible lines of descent, then there's still a probability of about 0.5 that you go extinct and about 0.5 that your lineage will persist. Here's a question. What difference does it make who starts the lineage? The calculations are based on the idea that the lineage is started by the birth of a new royal baby or something like that. So it started off the birth of an individual, but what if you could start a lineage with an individual of any age? Then you get this result. This is 1947 rates for Japan. If you start at age 0, you see the about 0.4 probability of extinction that we saw before. If you were to start the lineage with a single female age 60, the probability of extinction of that lineage is 1, because the female is not going to be able to produce any offspring. And you see how that probability shifts depending on who you start the lineage with. Now, this assumes you're starting the lineage with one individual. What if you could start the lineage with an individual and all of the descendants she already has? This is a picture of a birthday party for a woman named Shoshana Ovitz, who was 104 years old in 2019, and her family organized a party for her in Jerusalem with as many of her descendants as they could get to the party. It was a little over 400 descendants. If you think about starting a lineage at age 104, Shoshana Ovitz's lineage is not going to persist. If you think of starting a lineage with Shoshana Ovitz at 104 and all her current descendants, then it's a very different picture, and the lineage is going to persist. This is the version for Japan, where the multitude is from the Walt Whitman quote, "I'm large, I contain multitudes." And you can see that the older the initial individual is, if they get to bring all their descendants with them, then the probability of extinction goes down. Is that a useful calculation? I don't know, but. So I hope at this point that I've convinced you that there's a way to do formal demography of kinship, and that it boils down to this simple model with all of the ways to enlarge the model by incorporating other things in. I hope that it's also stimulated you to say, well, what about some other part? Because that's the other piece of formal demography, is getting to ask that question. There's lots of other things that I'm thinking about adding, and there's lots of things that I'm sure you're all thinking about adding, and I look forward to hearing about them, and thank you. Let's see.
So
there.
Thank you very much to Professor Caswell for that exciting and fascinatingly interesting talk. It's always great when you've got a talk that can combine matrix algebra and Lord of the Rings, so I think that's got to be a good combination. So we'll now invite some comments on that from our panel. So I'm delighted to welcome up to the podium for the first response Professor Jakob Biak. Jakob is a statistical demographer with a whole range of exciting interests, but I'll hand over to him. Thank you.
Thank you very much, and it's a great pleasure and honor to actually be able to comment on Professor Caswell's fascinating lecture. as part of this series. So in response, I'd like to make 3 main points. The first one is, as you may gleaned from the presentation, the work is very firmly rooted in the tradition, in the very long-standing tradition of formal demography. And Hal mentioned Galton and Watson in the talk, but there is much more to it, and and actually this tradition dates back at least to the middle of the 19th century, to Pierre-François Verhulst and his logistic model of population growth that was meant to describe formally the Malthusian population dynamics, which was quite a topic at the time. And then these developments gained pace in 1920s with thought leaders of the time, including Raymond Pearl and Alfred Lotka and many others. And this was something, at that point, there wasn't much of a difference between human demography and the demography of other species. So methods were evolving in parallel, and different communities were taking as much from those as they could. And this culminated in 1970s and early 80s with the work of Nathan Kefis and Andre Rogers, who developed these methods further. But since then, something slightly changed on the human side of things. So the further developments of formal mathematical models of population dynamics became mostly the preserve of population biology, ecology, and non-human analysis, whereas the center of gravity of the human demographic mainstream moved more towards analyzing survey data and associations within those. So all the more, it's fascinating to see how the work that Hal has presented is sort of making a full comeback with the discipline going back to its formal roots and reconnecting with them. The second point is slightly related to the first one, because it's a point about the gaps, the research gaps and the training gaps in contemporary human demography. So you have heard about some fascinating stories, not to mention the Lord of the Rings, in the lecture, but formal demography nowadays still remains a very niche topic at the fringes of the interests of human demographers. And besides, lots has been written, especially in the last few years, about the lack of theory in human demography, the theoretical paucity of the discipline as such. And the late Canadian demographer Tom Burge, who unfortunately passed away last year, in his 2018 book and earlier many essays that he wrote over the years, highlighted how mathematical population models are in fact the theory, are in fact explanatory mechanisms that allow us to understand how things work and how populations change. So models are theory. And to make the most of the opportunities that these models offer, what we need is more of a formal training in the tools that we require. In this case, this is the matrix algebra that we need. This is something that needs to be borne in mind by whoever is setting up the curriculum of training for future demographers. At the more advanced stage, mathematical calculus would be also nice to have. It's not necessary for these kind of models, but quite a lot of the traditional formal demography has been using that as well. And finally, the third point I'd like to make is that what Hal has presented is actually demonstrating very clearly not only the mathematical beauty of these models and approaches, but also that these approaches and their extensions, so matrix-based models, can be very versatile. And you have seen it even on the last slide with the possible extensions. There are many ways in which this can be very productively extended. This is not just a theoretical exercise, as much as these models can contribute to the further development of the demographic theory. This is also something that bears huge promise for practical applications, hopefully informing some real-life policies and developments further down the line. And these are exactly the things that the Connecting Generations Center is going to be exploring over the course of its running in the next 5 years. But as to the details, I'll hand over to my colleague, Dr. Joanne Ellison, who will present her reflections on some of the specific areas of application.
Thank you, Jakob, and thank you, Professor Caswell, for your talk. So as Jakob said, I'm focusing more on the applications. And so what I've been researching over the last few years has been looking at how we can build in parity information, so information about the previous number of live-born children, into fertility projection models. And so because of this, I'm particularly interested in the multi-state extension of Professor Caswell's matrix formulation to include age and something else, where this something else can be parity. And this is addressed in the second paper of the Formal Demography of Kinship series in 2020. And in this paper, Professor Caswell provides various reasons for why we might want to include parity as a state, including its influence on fertility, and as well as maternal, infant and child mortality, and also the ability to explore a wider range of kinship issues, like those related to the availability of informal childcare. And from a technical perspective, parity is relatively straightforward as a state, given its sequential nature, and also that offspring are necessarily born into parity 0. And as Hal mentioned, the human fertility database, the wealth of the available data is another advantage, where we have long time series of data on parity-specific rates by age of mother and also time. So in the context of fertility projection models, parity information is generally neglected, and projections typically are produced at the level of total births rather than births by birth order. However, the inclusion of parity has a similarly strong justification, with a particular focus on being able to mimic the decision-making process underlying childbearing, and so account for the important influence of the current number of children on the decision to have an additional child. So a crucial question is whether the additional complexity that we introduce into the fertility projections by including parity, whether that leads to more reliable forecasts. And our current findings show that it tends to improve both the accuracy of the forecasts and their precision. But even if the ultimate conclusion is that there isn't, only, say, a minor improvement, the richness gained through being able to express the overall fertility rate in terms of the parity dynamics that interact to produce it is of great value in and of itself. So going back to Hal's work, the flexibility of the matrix formulation means that, as well as being able to include extra states, the demographic rates can also be allowed to vary across time, which Hal skipped over because of time. But this is addressed in the third paper of the series from 2021. And this means that we can obtain kinship structures as outputs of routine population projections, such as those produced by national statistical agencies. And then furthermore, these demographic rate projections that are used as inputs can depend on additional states, such as parity. So in this way, advances in both fields, so the field of kinship modelling and the field of modelling and forecasting demographic rates, are mutually beneficial. And increased sophistication in kinship projection methodology, as we see from Hal, can encourage increased sophistication in rate projection methodology, and vice versa. So from the perspective of rate projections, this encourages the development of coherent, multi-state projection models with well-calibrated uncertainty, and the projections can then be incorporated into the kinship model framework to extend the outputs even more. So this potential to integrate developments in these two research areas provides a very exciting opportunity from both a methodological and a substantive standpoint.
So thank you both very much to both members of our panel for that really really insightful set of comments. So we heard from Jakob about the sort of the historical roots of this work and how this represents, a really exciting return to some of the work that's been going on in the area of formal demography previously, and also about the elegance and the simplicity of the models and the huge amount of detail and insight into some really important questions that we can get from them. And then also from Joanne on some of the specific applications in the area of parity and how that marries with the work that we've been doing over a long period of time, and the work that Joanne has been doing, really exciting work on forecasting kinship. So we're now going to throw things over to questions from the audience. Excuse me while I have a route around for those questions. So hopefully you should have so maybe I'll ask for questions from the in-person audience first, so I can see Jane over there.
Thank you very much. Thank you very much, Hal. Really exciting. So I was really struck by the application of this kind of work and thinking about the availability of kin. So Joanna mentioned the availability of kin for childcare. I'm thinking about the availability of kin at the other end of the life course. And I was struck by your graphs when you were looking at daughters by parity, that actually when you start getting up to age 70 or 80, the differences between the two time periods that you're looking at, I think it was for Japan, actually weren't that different because you've lost kin through mortality, but of course you're having fewer adult daughters. I was wondering whether those are period measures. I wondered if you thought about how you would incorporate cohort into this.
Yes, I have. Do you want me to just come up here, or I guess I'm mic'd.
Yeah, it's up to you.
Here.
Wherever you feel more comfortable.
Yeah, I'll wander over here. Okay. Thanks, Jin. That's a really interesting question. By letting the rates vary over time, as Joanne was emphasizing, you can map those rates and subject the kinship network to the changing rates as all of the members of that kinship network, whenever they started off, continue to develop under the different sets of rates. And you can, the past is just another version of the future, so you can keep going in connected up to a projection. Ji Song at the University of Pennsylvania and one of her students, Kai Feng, and I have been doing this calculation for looking at the availability of kin relative to the prevalence of dementia at older ages. So how many relatives of what kind and what ages would an individual have potentially available for care of an individual suffering from dementia, because we have data on the prevalence of dementia. And it gets at exactly, I think, what you're asking about. It lets you specify what history created this kinship network, what's the condition you're interested in knowing about, and then you get information on the availability of kin for potential care or help or information like that. So it's a thing that we're actively working on. Ji and Kai have really fascinating results on the case of China for that. And it should be generalizable to any kind of conditions.
Fantastic, thank you. So I'm going to read a question now from our online participants. So I have a question here that says, with parity, does this modelling allow us to look at the likelihood of intergeneral transmission of family size? So maybe I'll pass that on to
I presume by that, you, the questioner, hi, up there, means some kind of intergenerational correlation of family size. If you came from a big family, does that mean that you then produce a big family, or you produce a small family? It doesn't actually incorporate anything like that, because the information on parity-specific fertility doesn't track individuals. It's aggregate level rates of births by women of different parities, but you don't know what the parity conditions of their immediate ancestors were. You'd have to get a lot more individual level information in order to be able to do that. You could make up scenarios of intergenerational correlations. You could say, what if the correlation is negative? What if it's positive? And you could build that in, but it would expand just be another expansion of the model.
Thank you. Yes, sorry. Was there a question in the room? No. Oh yeah, Peter.
Yeah, thank you very much for your presentation and clearly laying out the kinship models, which you also clearly lay out in the papers, which I read with great interest. But what kept nagging in the back of my mind was, what about half-sisters? And so in the single-sex model, you clearly, all the half-sisters appear, but you don't get the half-sisters from the brother's side. And when you move to the dual sex, you also have these half-sisters and half-brothers. So should I worry, or is it, I sometimes think it's all just really covered in this, but then I go back and think about it again, and I get worried again.
By half?
I mean, so a sister of yours that doesn't have the same father.
So that's a thing that has not yet been put into the model. There is no the putting individuals together and bringing their relatives with them would be one way to sort of account for the joint ownership of a kinship network by two people. The other thing that's not so step relatives or half relatives or things like that aren't in the model yet, and I think that's one of the really interesting developments to look for, because it's tricky. As I'm sure the reason it's nagging in the back of your head is that it's tricky to know how you would combine those individuals.
Because when you're looking at the woman-focused one, then half-sisters do appear, because you're looking at the sisters of a mother. Yes, so you will. In your model now, the half-sisters will be present from the mother's side.
Yeah, in the single-sex model, the sisters of Focal are the daughters of Focal's mother.
So they could be sisters or half-sisters.
Yeah.
I'm glad it's not a straightforward answer. I'll think about it some more.
Fantastic. Right. Well, I'll go to another question from online. In fact, we have a sort of a cluster of questions on a similar sort of topic. So we have a question that asks: Do models allow for interactions between processes? So, for instance, how might parity affect life expectancy? And can model outputs be easily stratified to see the effect of education on both fertility and mortality dynamics? So some questions about how these processes might interact, and the interaction between rates and kin and outputs.
Good questions. So there's sort of two different. The two questions are looking at two slightly different aspects of the situation. So in the model, when you incorporate parity becomes a state variable. You know not just the individual's age, but you also know her parity. And you have to incorporate the effect of the individual's state on their probabilities of survival and reproduction. When you go to the human fertility database, you can find age and parity-specific fertility rates, but you don't find age and parity-specific mortality rates. And I tried looking this up, like, is there a cost of reproduction? Do women who have lots of children have different mortality schedules than women who don't? As near as I could tell from poking around in the literature, the answer is we're not really sure. And so in that version of the model, the mortality schedule is the same regardless it's only a function of age. It's independent of parity. But if it did depend on parity, then you could build that in, and that would give you parity, age and parity-specific life expectancy information. The other question about stratifying has two basic things. One is you could do, as is often done in stratifying other kinds of demographic processes, you could say, I have low, medium, and high educational groups, and I have the rates for low, medium, high educational groups. I can calculate the consequences of the mortality and fertility that comes with those, and I have three separate kinship outputs. Or you could build educational status in as a state variable and allow individuals to move as they age through different kinds of educational stages. Then the kinship network around a focal individual is now structured by both age and educational attainment in some way. Obviously, that takes a whole lot more information than just saying these education groups have different rates, so I'm going to look at each one of them. But you could do either of those just depending on what kind of information you know.
Maybe if anyone from the panel has anything on, or any comments on anything that comes on that. No, okay. Well, I think we'll make the best use of Professor Caswell's answers here. Bernice, a question here. Thank you.
Hi, really interesting talk. Thank you. This kind of piggybacks a bit on what you were saying about education, but I was wondering about partnership, because in the beginning of your talk, you said members can be either reproduced or recruited, and I'm guessing, recruitment is, partnership is one of the ways you recruit new members, and it's especially pertinent when we talk about things like kin networks for support and resources. So could you talk a little bit about how partnership fits into this, and obviously it ties into fertility and mortality as well?
So another really good question, and another extension of the model that hasn't happened yet. There exist really nice models describing partnership transitions, different kinds of versions of what constitutes the different stages of partnership, both marriage and non-marriage and divorcing and all that. One of the nicest looking analyses that I know of belongs to Melinda Mills. Are you out there, Melinda? Who's part of this project, who did really nice multi-state models for the movement of individuals through partnership stages as a function of their age. And if we had those matrices, we could put them right into the kinship model the same way that the parity transitions go in, and then you would have indeed information on the kin of different partnership statuses and how those change, and it would be a fascinating thing to add to the model.
I think. Maybe Jane first, and then Tamin. Yeah.
Thank you. This is really a reflection rather than a question. Is when we move from macro simulation modelling to micro simulation modelling. So how many different states does it take that for us to then move our toolkit? It's
I think, it's the case that you need the same states for a microsimulation model that you do for a macro simulation model. If you think that education level affects things, then you need to keep track of educational level in your microsimulation model or in your matrix. If you think that relationship status affects things, then you have to incorporate that. The extra added value in a microsimulation model is that you can build in different kinds of interactions between individuals that are very hard to incorporate into the sort of more macro dynamic models context, because you actually have the individuals moving around and you can let them interact with each other. But the state variables you need, I think, are the same.
Thank you. I'm going to hand over to Min.
Yeah, thank you for the great talk. I was wondering, the model consider fertility and mortality, whether it could consider the quality of the network, kinship network. For example, the geographic distance of the children, like it is available for the social care provision, particularly for the population aging.
Yeah, so it is possible to build one of these models where you have individuals characterized by, let's say, their age and their location. If you have some set of places where they could be, and that would go into the model in the same way that parity could go into the model, or that education level or relationship status could go in. And then you have to decide how you want to describe. So in the parity case, and Joanne mentioned this, that it's particularly easy because everybody's born into parity class 0. You know, everybody starts off at the same place. If you have multiple locations, where do births go? Who produces new relatives in what places? And then you let the individuals move. You would need a migration model to go with it. It's both a biologically interesting question. Animals move around, and that's a really important part of their adaptations. And humans move around as well. So that's something that needs to be built in or explored with the model.
Fantastic, thank you. Right, well, I think we're there's plenty more exciting questions around, but I think we're running towards the end of our time. I'm going to invite a very quick point here from Jakob before I sum up and close. But yes, so I'll let you.
Thank you. So as you have heard in the talk and in the discussion, there was a mention of a series of 4 papers so far. All of them have appeared in demographic research and are available open access on the journal's website. I need to declare interest here as the journal's current editor, but equally I wanted to say that we are really delighted to be able to host this collection in our pages. Thank you very much.
And there's more coming.
So yes, so on that note, thank you everybody for the fantastic discussion today. I think as the audience questions and as Jakob and Joanne have highlighted, this is a really important contribution to the discipline. And it marks a step change in terms of what is possible in the modelling of kinship. And at the Collecting Generations Centre, we're going to be working with some of Hal's methods to answer some of the really important and pressing questions that we're facing today. So we're really indebted to him for developing this really exciting family of methods. So that brings us to the end of today's talk. So thank you very much to Professor Caswell for his insightful talk. And thank you also to everybody who's logged in or turned up today to listen to the talk, and also to the team who's made everything happen smoothly today as well. And yes, we should have some details, I think, of our next talk. They're probably, yes, they'll be flashing up on your screen if you're watching online. I thought they might be on this screen, but so yes. So please do sign up and register to those talk details to those talks, and we'll have some more exciting talks for you along shortly. And you will also see, if you're online, a short poll on your screen, which we'd kindly ask you to spend a couple of minutes just helping us out and telling us how we did today. And the final thing is that we'll be sharing the footage of today's event as well, so keep an eye out for that. Otherwise, thank you very much everyone for joining us, and enjoy the rest of your days.